Welcome to the deep dive. Think about it. Every single day you're looking through lenses, maybe in your glasses or, interacting with reflections in mirrors.
Absolutely. And today we're going to unpack the physics behind these everyday things, mirrors and lenses.
Yeah, consider this like a shortcut, right? A way to really get how reflection and refraction actually shape the images we see all the time.
Exactly. We're pulling from a really solid college physics textbook here. The idea is to get to the core principles and maybe uncover some surprising ways these basic concepts show up in, well, the tech all around us.
Okay, great. So let's dive right in with something super familiar. Flat mirrors, like the one in your bathroom. You see yourself, looks like you're behind the glass. How's that image actually, formed?
Okay, so it all starts with light. Light rays leave you, the object, hit the mirror surface and bounce off. That's reflection.
Right.
Then your eyes intercept those reflected rays. Your brain kind of traces them back in straight lines and assumes they came from a point behind the mirror.
Ah, so that point behind the mirror is the image.
That's your image, exactly, an apparent source.
Okay, so there are these two distances then. How far you are from the mirror, that's the object distance, Barry, right?
Yep. Yeah.
And then how far the image looks like it behind the image distance Q. What's the deal with P and Q for just a normal flat mirror?
For a flat mirror, it's actually beautifully simple. The image distance Q is exactly the same as the object distance P. Well, same magnitude.
So if I'm 1 meter away, my reflection looks like it's 1 meter behind the mirror.
Precisely. It's like a perfect one-to-one spatial mapping just flipped.
Okay, that makes sense. Now, this idea of real versus virtual images comes up a lot. My reflection seems real enough, but I obviously can't shake its hand. What's the actual difference?
Yeah, this is really fundamental. A real image is formed where light rays physically converge, like they actually cross paths at a point in space.
Okay.
So if you put a screen, say a piece of paper, right at that point, you'd see the image projected onto it. Think of a movie projector.
Right. You can see it on the screen.
But a virtual image, like your reflection in a flat mirror, is different. The light rays appear to diverge from a point behind the mirror, but they don't actually meet there.
Ah, so the light isn't really back there.
Exactly. Your brain extrapolates the rays backward. That's why you can't project your reflection onto a screen. It's virtual.
Okay, virtual image. Got it.
Yeah.
What about the size? Does the mirror make me look bigger or smaller?
Good question. We talk about object height, h, and image height, h prime.
H prime.
And
Yep.
the ratio between them, h prime divided by h, is called the lateral magnification, m.
Magnification M makes sense.
For a flat mirror, the image height is identical to the object height, so h prime equals h.
Meaning M equals.
M equals 1, which just means the image is unmagnified, same size as the object.
Right, okay. So summarizing flat mirrors, they give us a virtual image. It's unmagnified,
Yep.
M1, it's upright, and it's located as far behind the mirror as the object is in front.
Perfect summary.
Okay, but hang on. This makes me think about my car's rear view mirror. The little tab you flip for day and night. How does that work? That seems more complicated than just a flat mirror.
That's a fantastic practical application. It's actually quite clever. Most rear view mirrors aren't just a single flat piece of mirrored glass.
Oh.
They're typically a wedge of glass, slightly thicker at the top or bottom, with the reflective silvering on the back surface.
On the back, okay.
So during the day, light from a car behind you goes through the front glass surface, refracts a bit, hits the highly reflective back coating, reflects strongly, comes back through the glass, refracts again, and then into your eyes.
Giving you a nice bright view.
Exactly, a bright reflection from that back surface.
So what happens when I flip the little tab for night driving?
When you flip that tab, you're tilting the entire wedge assembly slightly.
Just a little bit.
Just a little bit. But that small tilt is enough to aim that bright reflection from the back surface upwards, usually towards the car roof so it doesn't hit your eyes directly.
Ah, so it misses you. But you still see something, right? A dimmer reflection.
You do. What you see then is the reflection from the front surface of the glass wedge.
The glass itself.
Oh,
Before the silvering.
precisely. Glass itself reflects a small percentage of light, maybe 4% or so. That front surface reflection is much, much dimmer than the one from the silvered back.
So it cuts down the glare from headlights.
Exactly. It's bright enough to see there's a car there, but not blindingly bright. It cleverly uses both reflections, and the tilt just selects which one dominates your view.
That's really neat. It's using reflection and refraction because the light bends going in and out of the glass wedge.
Yep, both phenomena are involved.
Okay, cool. Let's curve things up now. Spherical mirrors. What's the story there?
Well, as the name suggests, they're mirrors shaped like a section of a sphere. Imagine cutting off a piece of a mirrored ball.
Okay.
If the inside surface is reflective, it's a concave mirror. Think, like the inside of a cave or a bowl.
Concave holds water. Got it.
And if the outside surface is reflective, it's a convex mirror. It bulges outwards.
Like the back of a spoon.
Exactly like a spoon. That's the classic example.
So concave and convex. Let's focus on concave first. What are the important bits we need to know? Terms and stuff.
Right. Key terms. There's the radius of curvature, r, which is just the radius of the sphere the mirror was cut from.
Okay.
There's the center of curvature, c, which is the center of that original sphere.
Makes sense.
The vertex, v, is the geometric center of the mirror surface itself. And the principal axis is the straight line that runs through both c and v.
The main center line.
Yeah. Now, how light reflects is interesting. A ray going straight through the center of curvature, c, hits the mirror head-on, perpendicular, and reflects straight back along its path.
Bounces right back.
And here's a crucial one. For rays close to that principal axis, this is an approximation, but a good one for spherical mirrors, rays coming in parallel to the principal axis all reflect and converge at a specific point.
A focusing point.
Exactly. That's called the principal focal point, F. And conversely, rays passing through the focal point before hitting the mirror will reflect parallel to the principal axis.
Okay, so parallel rays go to the focus, rays through the focus go parallel. Nice symmetry.
And of course, the basic law always applies. Angle of incidence equals angle of reflection wherever the ray hits.
Always. Okay, so R, C, V, F, principal axis. Lots of geometry. Is there an equation that ties object distance P and image distance Q together for these curved mirrors, like we had for flat ones?
Yes, there is. It's fundamental. It's called the mirror equation. 1 over P plus 1 over Q equals 2 over R.
1P plus 1Q equals 2R. Okay? That connects object, image, and the mirror shape.
Precisely. It lets you calculate where the image will form.
And magnification. Is it still M equals H prime over H?
It is, yes. The definition MHH still holds. But for spherical mirrors, we also have another way to calculate it. M equals minus Q over P.
M equals minus Q over P.
M equals minus Q over P.
M dash QP.
Right.
Why the minus sign?
The minus sign is important. It tells us about the image orientation. If M comes out negative, the image is inverted upside down compared to the object.
Inverted? Whoa. So unlike a flat mirror, a concave mirror could actually show me upside down.
Absolutely. Depending on how close or far the object is from the mirror relative to C and F, you can get images that are real or virtual, upright or inverted, magnified or smaller.
Lots of possibilities.
Definitely. We need rules, sign conventions to keep track. But before that, maybe quickly mention spherical aberrations.
Spherical aberration sounds like a vision problem.
Sort of related to clarity. It's a limitation of spherical mirrors. They're easy to make, but they aren't perfect focusers.
How so?
Rays hitting the mirror far from the principal axis don't quite converge at the exact same focal point as rays hitting near the center.
So it's not one perfect point.
No, it's slightly spread out, leading to a bit of blurring or fuzziness in the image. That's spherical aberration.
Is there a fix?
Well, parabolic mirrors do focus parallel rays perfectly to a single point. That's why they're used in, say, big telescopes where sharpness is critical, but they're harder to make.
So spherical is often a good enough, easier to make approximation.
Especially if you only use the central part of the mirror near the axis.
Okay. Back to the mirror equation. 1P plus 1Q equals 2R. You also mentioned the focal point, F. How does its distance, the focal length, F, relate to R?
For spherical mirrors, again, assuming rays near the axis, the focal length F is simply half the radius of curvature, so F equal R2.
F R2. Simple enough.
And this lets us write the mirror equation in maybe its most common form. 1P plus 1Q equals 1F.
Using focal length instead of radius. 1P plus 1Q equals 1F. Got it.
This F is positive for concave mirrors because they converge light to a real focus in front of the mirror.
Okay. So what about the other type, convex mirrors? The ones that bulge out.
Right, convex mirrors. They're also called diverging mirrors. When parallel light hits them, it reflects outwards, spreading out.
Diverging, spreading. Okay.
The reflected rays look like they're coming from a focal point behind the mirror.
Behind the mirror again. So
yeah.
Virtual focus.
Virtual focus, yes. And because the reflected rays themselves don't actually converge, convex mirrors almost always produce virtual images.
Virtual, like flat mirrors. So you can't project the image from a convex mirror either.
Correct. They typically give you an upright virtual image that's smaller than the object. Think of those security mirrors in shops.
Ah, yeah, they give a wide view, but things look smaller.
Exactly. Now, to handle all these cases, concave, convex, real, virtual, upright, inverted, we absolutely need sign conventions.
The rules for plus and minus signs.
Yes. They tell us things like object distance P is usually positive if it's in front of the mirror. Image distance Q is positive for real images in front and negative for virtual images behind.
Okay.
Focal length F is positive for converging concave mirrors, negative for diverging convex. Image height H prime is positive if upright, negative if inverted.
And magnification M follows that positive for upright, negative for inverted.
You got it. Sticking to these conventions is crucial for the equations to give you the right answers that match reality. It's like the grammar of optics math.
Okay, got to remember those sign rules.
Yeah.
Phew. Right, we've covered reflection pretty well. Let's switch gears to refraction. Light bending when it goes from one material to another. How does that form images?
Right, refraction. So imagine light going from, say, air into water or air into glass across a curved boundary, a spherical surface between the two.
Like the surface of a lens, maybe?
Could be, yeah. Or just light entering a sphere of water. If the surface has radius r and the materials have refractive indices n1 and n2.
Refractive index? And that measures how much the light bends, right?
Exactly. n1 for the first medium, n2 for the second. The equation relating object distance p and image distance q is n1 over p plus n2 over q equals n2 minus n1 all divided by r.
Whoa, okay. N1p plus N2q equals N2 N1r? That looks more involved than the mirror equation.
It is a bit, yeah. It accounts for the bending based on both materials and the curvature.
And magnification for these refracting surfaces.
The magnification m equals hh is given by minus n1 times q divided by n2 times p. So m equals n1q, n2p. Notice the n's are in there too.
Okay, the indices affect the size too. What if the surface isn't curved? What if it's just flat, like looking into a fish tank?
Great question. A flat surface means the radius of curvature r goes to infinity.
Infinity.
And if r is infinite, that n2, n1r term in the equation becomes 0.
Right. Anything over infinity is 0.
So the equation simplifies a lot. It becomes just n1p equals n minus n2q.
N1p equals N2 N2q.
Or you can rearrange it. Q raises n2 n1p. The key thing is the minus sign in the ratio of the n's. It tells you the image distance q is negative.
Negative q means virtual image.
Virtual image, and it also means it's on the same side of the surface as the object.
Same side. Wait, so when I look into a pool, the bottom looks shallower. Is that this?
That is exactly this. Light comes from the bottom. Object P is its real depth. Goes from water N1 and 1.33 into air N2.1. Your eye sees a virtual image Q that's closer to the surface. Q equals 11.33 P, so the apparent depth Q is less than the real depth P.
Ah, cool. So that apparent shallowness is a direct result of this flat surface refraction.
Yep. And just like mirrors, we have sign conventions for refracting surfaces too, defining what's positive, negative for P, Q, R, and H to keep everything consistent.
Right, always the sign conventions. So refraction isn't just some lab concept. It's literally changing how we see the world through water or even air.
Absolutely. Atmospheric refraction is a huge one. Air isn't uniform, it's density, and therefore its refractive index change with altitude, temperature.
Okay.
So sunlight entering the atmosphere doesn't travel in a perfectly straight line. It bends.
It bends. How does that affect things?
Well, one amazing effect is that you can still see the sun for a few minutes after it's actually dipped below the geometric horizon.
Really? How?
The light rays from the sun just below the horizon bend downwards as they pass through the denser lower atmosphere, reaching your eyes as if the sun were still slightly higher up.
Wow. So the atmosphere acts like a giant weak lens.
In a way, yeah. It bends the light path. Mirages are another example.
Oh yeah, the shimmering water on a hot road?
Exactly. That's not water. It's caused by extreme temperature differences near the road surface. Very hot air near the ground is less dense, has a lower N. Light from the sky heading towards the road gets bent upwards as it enters this hot layer.
Bent upwards?
Yeah, strongly refracted.
Yeah.
So strongly that the rays that would have hit the road instead curve up towards your eye, looking like they came from the ground. Your brain interprets the skylight coming from the ground as a reflection, like from water.
That's fascinating, just bent light from the sky. Okay, amazing examples. Let's move on to lenses proper. Shaped glass or plastic pieces. We use them everywhere. Glasses, cameras, microscopes. What are the basics?
Okay, thin lenses. Usually glass or plastic with two refracting surfaces. These surfaces can be spherical or sometimes flat.
Two surfaces, Mel.
Two surfaces. And they fall into two main camps: converging lenses and diverging lenses.
And converging and diverging. What's the difference in shape?
Converging lenses are thicker in the middle than at the edges. Think of a classic magnifying glass shape.
Right, bulges out in the middle.
Diverging lenses are thinner in the middle and thicker at the edges, kind of concave on both sides or flat on one and concave on the other.
Thinner in the middle, okay. And they do what the names suggest.
Pretty much. Converging lenses take parallel light rays and bend them inwards to meet at a focal point, F, on the other side.
They converge the light.
Yep. The distance from the lens center to that focal point is the focal length, F. It's positive for converging lenses.
Then diverging lenses.
They take parallel rays and bend them outwards, making them spread apart.
Diverge.
Right. These diverging rays appear to come from a virtual focal point back on the same side as the incoming light. So diverging lenses have a negative focal length, F.
Virtual focus again, negative F. Okay, so lenses have focal points and focal lengths too, just like mirrors. Is there like a lens equation similar to the mirror equation?
Amazingly, yes, and it's mathematically identical. For a thin lens, the relationship is 1p plus 1q equals 1.
The exact same form.
Yeah.
1p plus 1q equals 1f. That's convenient.
It is. And the lateral magnification, m, is also given by the same formula as for mirrors. M in charge h dash qp.
M equals dash qp again, minus sign, meaning inverted images are possible.
Correct. The physics principles are different, refraction versus reflection, but the geometry of how object and image distances relate for simple thin lenses and spherical mirrors ends up looking the same mathematically.
That's pretty neat. But where does the focal length f of a lens actually come from? With mirrors, it was R2. What determines f for a lens?
That depends on how the lens is made. It's given by the lens maker's equation.
The lens maker's equation. Sounds official.
It is. It says 1f equals n1 times 1 over r1 minus 1 over r2.
Oh, okay. 1f equals n1, 1r1, 1r2.
Yep.
Let's break that down. N is the refractive index of the lens glass.
Yep. Relative to the surrounding medium, usually air, so n is just the glass's index.
Then R1 and R2 are.
The radii of curvature of the two surfaces of the lens, R1 for the first surface the light hits, R2 for the second.
So the shape of both sides matters.
Absolutely. And again, there are sign conventions for R1 and R2 depending on whether each surface is convex or concave relative to the light path.
Of course, more sign conventions.
Gotta have them.
Yeah.
But this equation shows how lens makers can design a lens with a specific focal length f by choosing the glass type, which sets as n, and carefully grinding the curves, R1 and R2.
So they can engineer the focal length precisely. That's cool. Now, if I want to figure out where an image will be, besides using the equation, are there ways to, draw it, ray tracing?
Yes, absolutely. Ray diagrams are super helpful for visualizing image formation with lenses. There are 3 principal rays that are easy to draw.
Okay, what are they? For converging lens first.
Sure. For converging lens, 1, a ray coming in parallel to the principal axis refracts through the focal point F on the far side of the lens.
Parallel goes through far focus.
Got it. 2, a ray passing right through the center of the lens goes pretty much straight through, undeflected, assuming it's a thin lens.
Through the center, keeps going straight. Okay.
3, a ray that goes through the focal point on the near side, the object side, refracts and comes out parallel to the principal axis on the far side.
Through near focus, comes out parallel. Okay, the reverse of the first one.
Exactly. Where these 3 rays, or sometimes their extensions, if it's a virtual image, intersect, that's where your image is formed. You can see its location, size, and whether it's upright or inverted.
Nice. And for diverging lenses, similar idea?
Similar idea, but using the virtual focal point. A ray parallel to the axis refracts as if it came from the near side focal point. A ray aimed towards the far side focal point refracts parallel, and the ray through the center still goes straight.
Okay, so drawing those helps picture the outcome. What if you have multiple lenses in a row, like in a camera zoom lens or a microscope?
Good question. You just treat them one by one.
A step by step.
Yeah. Find the image formed by the first lens. That image then becomes the object for the second lens. Find the image formed by the second lens. That becomes the object for the third, and so on.
Okay, so you chain the calculations or the ray diagrams together.
Exactly. The image of one is the object for the next.
Right. Now, we've been talking mostly about ideal mirrors and lenses, but you mentioned spherical aberrations earlier for mirrors. Do lenses have problems too? Imperfections?
Oh, definitely. Real-world optics have limitations. Spherical aberration affects lenses too, for the same reason. Spherical surfaces aren't perfect focusers, especially for rays far from the center, causes blurring.
Same blurring issue. How do cameras deal with that?
Well, one way is the aperture, or diaphragm. By stopping down the lens, making the opening smaller, you block those outer rays and only use the central part of the lens, which focuses better.
Ah, using a smaller hole.
Right. The trade-off is you let less light in, so you need a longer exposure time or more sensitive sensor.
Makes sense. Any other lens problems?
Yes, a big one is chromatic aberration.
Chromatic, like color.
Exactly. It happens because the refractive index in of glass isn't actually constant. It's slightly different for different wavelengths or colors of light.
Wait, glass bends different colors by different amounts.
Yep. Blue light usually bends a bit more than red light, for example.
So what does that do to the image?
It means a simple lens can't focus all colors at the exact same point. Blue might focus slightly closer to the lens than red.
Ah, so the focus is smeared out by color.
Exactly. It leads to color fringing, especially noticeable around high contrast edges in a photo like purple or green outlines. Degrades sharpness.
That sounds like a problem for cameras and telescopes. How do they fix that?
Cleverly. They often use compound lenses made of 2 or sometimes 3 different types of glass cemented together.
Multiple pieces.
Yeah, an achromatic doublet is common. It pairs a converging lens of one type of glass with a diverging lens of another type. The types of glass and their shapes are carefully chosen so that the chromatic aberration of one element largely cancels out the aberration of the other for at least 2 primary colors, say red and blue.
Wow, so they use one error to cancel another error out.
Essentially, yes. More complex designs, apochromats, can bring 3 colors to the same focus. It's all about managing these unavoidable physics effects.
So designing really good lenses is actually a pretty complex balancing act, dealing with these different aberrations.
It really is. It involves careful material selection, precise shaping of multiple surfaces, and often trade-offs between different kinds of corrections.
Well, this has been genuinely illuminating, a real deep dive into mirrors and lenses.
Glad we could shed some light on it.
Yeah. We went from basic flat mirrors, reflection, virtual images, then curved mirrors, the mirror equation, that spherical aberration issue.
Then shifted to refraction, how light bends, the pool example, atmospheric tricks like mirages and sunsets.
Right. And then thin lenses, converging, diverging, the lens equation, which looks so familiar, and the lens maker's formula.
Finishing up with those pesky but important aberrations, spherical and chromatic, and how designers try to fight them.
It really is amazing how these, fundamental physics principles are behind just seeing yourself or using a magnifying glass.
And think about how they scale up telescopes, microscopes, cameras, projectors, fiber optics. It all comes back to controlling reflection and refraction.
Absolutely. So maybe a final thought for everyone listening. Next time you catch your reflection or put on glasses or use a camera, just, take a second. Think about the light rays bending and bouncing according to these rules we talked about.
Yeah, and maybe wonder, how do the really advanced optical instruments work? How do they push these principles to the limit to see farther or smaller, overcoming those aberrations to give us incredibly detailed views of, well, everything?
That constant quest for a clearer picture, something to chew on. Thanks for diving deep with us.